This example actually has two problems in it, so we'll treat them independently. The first problem asks, let's suppose a man is trying to move a desk with a mass of 100 kilograms. And let's suppose the static frictional force between the desk and the floor is 196 newtons. How much force must the man apply in order to get the desk moving? So the first thing we have to worry about is what's the total force acting on the desk? Well, the worker is pushing on the desk, so that's a force, but friction is also resisting the motion, so that's a force. There are two forces and they oppose each other. So the total force is the worker's force minus the static frictional force. Now we know what the static frictional force is. It's 196 newtons. So let's go ahead and put that in the equation. Now in order to get this desk to move, the total force acting on the desk must be greater than 0. Therefore, the worker's force must be just a little greater than 196 newtons. That way, when you subtract 196 newtons from it, you still get a positive answer, which means there is some force acting on the desk. So the worker's force must be just greater than 196 newtons. But that's not quite the end of the story, because force is a vector. We want the desk to move west, so the force the worker applies must be just a little greater than 196 newtons west. Okay, that wasn't so bad. The next part's a little trickier. The next part says, let's suppose that desk is moving. Well, if the desk is moving, then we know we need to use the kinetic frictional force, and that's given as 110 newtons. Also, we're told that the box is accelerating with an acceleration of 1 meters per second squared. And the question is, what force must the man apply to keep this acceleration going? Well, once again, we have to consider the total force acting on the desk. The kinetic friction opposes the worker, so the total force is the worker's force minus kinetic friction. Now we're told what kinetic friction is. It's 110 newtons, so we might as well put that in there. So the total force is the worker's force minus 110 newtons. But we know another way of calculating total force. We also know that total force is mass times acceleration. Well, we were given the mass, 100 kilograms, and we were given the acceleration, 1.0 meters per second squared. So we can put those into the problem as well. So we know that the total force is 100 kilograms times 1.0 meters per second squared. That works out to 100 kilogram meter per second squared. That's the same thing as 100 newtons. So what do we have here? We know that the total force is 100 newtons. We can put that into our equation above. So we now know that the total force, 100 newtons, is equal to the worker's force minus 110 newtons. So in the end, we have an equation here that says 100 must equal whatever the worker's force is minus 110. Well, if you think about it, the worker's force has to be 210 for that to work. So the worker's force is 210 newtons. That's not quite the end of the story, though, because the worker wants his desk to go west, so we have to include that direction. So the worker's force is 210 newtons to the west.